Alright, today we're going to look at using Newton's laws to solve problems. We have the three Newton's laws. We're going to put them all together into some more substantial problems, so let the thinking begin. Then tomorrow we'll introduce kinematics to it as well. So we've got lots of fun things to do. So just a reminder, for all of these, their success criteria is going to be draw a free body diagram, choose your positive directions, write an F-net equation based on the diagram. So this is really important. I'm going to say that again and again and again. It's based on the diagram, so learn to make a really good diagram. Substitute values for F equals MA and F-net into the F-net equation, and we solve. So let's start with something fairly basic. A 40 kilogram mass has an external force of 120 newtons east acting on it. What is the acceleration of the object? Okay, there's a couple assumptions here. I'm not given any information about this yellow box moving up or down, so I'm going to just do some quick assumptions that the vertical forces, the normal force and the gravitational force, are going to balance, so I'm not going to deal with that. In grade 11, everything should just be in one direction, so expect some of those things to cancel. Grade 12, we'll start changing that up. So draw a free body diagram. I have it. If I wanted to add these two pieces, I can, but I already know they're going to balance because I'm not given any information about this object moving, so I'm not too worried about that. Okay, so if I look at my F-net equation, F-net equals the only force here is the applied force, and I'm going to use a convention that to the right is positive. So F-net equals Fa, the applied force. If I replace F-net with mass times acceleration and Fa with 120 newtons, okay, I'm on my way to start solving for the acceleration. The mass of this box is 40 kilograms, so I can substitute that in. And when I solve for A, I end up with 3 meters per second squared. That's the acceleration of the yellow box due to the 120 Newton force. Okay, so let's make it a little more challenging. We have a 40 kilogram mass. It's broken up into two pieces. We have a 30 kilogram piece and a 10 kilogram piece, and they are linked with a length of chain. If the same 120 Newton force is applied, what is the tension force in the chain? Okay, so we are looking for the tension force in that chain right there. Okay, so this is similar to the previous question, but with a little twist. So I have two columns here called parts and system. So if I look at parts, here's the small box in the back, which is the 10 kilogram box. The forces that act on the 10 kilogram box. We can agree there's an F normal and an FG, but we've already talked about we expect those to cancel because there's no information about this box jumping off the ground or flying around or anything. The next forces would be the tension force, so Ft, okay, and we're not given any information about the friction in this system or this question. So if there was friction, we would include an arrow going backwards for friction, but there's nothing in this question regarding friction. Okay, so if I go in here, I'm just going to erase these guys for now because I know I don't need them, but I do need the space to write. So if I write my F-net statement for the 10 kilogram box, okay, I could say, well, the F-net equals the tension force. I can replace F-net with MA, and then I can say, okay, the mass of that is 10 kilograms. But I run into a small problem because I don't know the acceleration and I'm looking for the tension force. So that's a dead end. Okay, let's draw the larger 30 kilogram box. I'll ignore the vertical forces. Let's use blue for our forces. So we have the 120 Newton force here. Okay, and then here's the key piece. We have an arrow going backwards that's also Ft. So when we write our F-net expression, we would have 120 minus Ft. Okay, now again, I replace the F net with MA. I'm just going to skip a line and jump ahead to say this is 30A equals 120 minus FT. Okay, so again, I have an equation with two unknowns that I can't solve. Okay, and at this point, you might think you're stuck, but we also have this system idea. Okay, so where we can take this whole thing and say if that chain doesn't stretch or bend or has no mass, then we could draw this whole system, the whole thing together, and call it a 40 kilogram mass. Okay, and we can say there's 120 Newton force acting on that, and what you should recognize is, hey, that's the exact same question we did back here. So when we view the problem that way, we now know the acceleration of that system is 3 meters per second squared. Okay, so now we can take that system information, and because these are linked with a chain that's not going to stretch, it's not dynamic, then that acceleration has to apply to both the 10 kilogram and the 30 kilogram mass. Okay, and that's a key piece for thinking about these problems. So I'm just going to take that 3 that I got from the system, and I'm going to insert it into our first setup for the 10 kilogram box. And what we'd find is there is a tension force of 30 newtons. Okay, now if I go back to the 30 kilogram box, if I put a 3 in for that A value, and I solve for the missing FT, you probably won't be surprised to see, and I'm going to rewrite FT on this side and go 120 minus 90, and no surprise there, because it has to be the same tension force because it's shared between the two. I got 30 newtons for both. Now you wouldn't do both boxes here. You would just do one of these, either the 10 kilogram or the 30 kilogram, but I wanted to show you that no matter which one you do, you get the same answer. But the key is there is a part and there is a system thinking process that we have to get our head wrapped around. Okay, so if you want to pause and try this, these are kind of fun. These mess people up. Mostly C messes people up, so just pause and give this a try. It's just asking for the tension in the string. Okay, so let's look at the first situation. If we were to draw a free body diagram, okay, and we have that right here, we have tension in the string is balanced by the gravitational force. None of these boxes are moving, they're all static. So the tension in the string must match the gravitational force. So it's 120 newtons. Okay, so if we move on to B, B has a pulley introduced into this problem. And a pulley, and I'll highlight this, I'll even slide it down right now. Get rid of that screen and make that go up. Pulleys, right here, the pulley, all it does is it changes the direction of the force. Okay, so this pulley here, if there's 120 right here, okay, which is the exact same, if we just looked at that little piece, if we just modeled that right there, it's that picture. Okay, so now the pulley, all that does is say, hey, take that force and change the direction so that it goes this way. Okay, so the tension in the string is still 120 newtons. Okay, now the third one, C, is the one that most people get wrong because they say, well, this is 120, this is 120, therefore if you went right here it should be 240. And you would be absolutely incorrect. Okay, and it's just natural to think 120 plus 120 is 240, but that's not the case. At that location right there at the very top, okay, you have a 120 and a 120 in equal magnitude, opposite direction. They balance each other out, and that's why the system doesn't move. Okay, if you were to put a wall right here, you would go back to number or letter B here. It would be the same model. So that tension in that string is 120 for all of them. And I'm just going to mark this right here. Pulleys just change the direction of the force. When we get to our energy section, we'll talk more about pulleys. Okay, this is one of my favorite questions, the sled question. Okay, so we have 3 sleds tied together, sled 3, 2, and 1, and they all have different masses. The mass of sled 1 is 12 kilograms, so I'm just going to take a second here. I like to write these things down as I go. The mass of sled 1 is 12 kilograms, the mass of sled 2 is 11 kilograms, and the mass of sled 3 is 7 kilograms. So the first question, oh, and we should note this, there's no friction acting on the sleds. That's a really important piece. So determine the acceleration of the sleds. Okay, so when we look at these types of problems, you could look at individual parts, or you could look at this as an entire system. So we could look at this whole group of sleds as one giant box or one giant system. Okay, so if I look at my system, and I draw a free body diagram of the system. If we add that up and hopefully do it correctly, it's 30 kilograms as a system. I have 120 newtons pulling to the right, and there is no friction, so I don't have to introduce that vector onto my free body diagram. If I write my F net statement, and I'm going to say positive is to the right, F net equals the 120 newtons, because that's the only force. If we replace F net with MA, then we have 30 times A equals 120, and I get an acceleration of 4 meters per second squared. So there's the first one done. Calculate the magnitude of the tension in rope A. So let's go with blue for rope A. That's this one right here. Okay, so I'm going to draw a free body diagram for sled 3. The only force acting on there is the force of tension from rope A, and it is 7 kilograms. So if I write an F net statement, I have this tension force here of FTA. Okay, F net can be replaced with mass times acceleration. The mass is 7. And now we already found the acceleration over here of the system, and that means that all of the parts will be moving at the exact same acceleration. So I can put a 4 in there, and the tension force due to rope A is going to be 28 newtons. Okay, and now let's go to purple, and no, we did purple, let's do green, and we'll calculate the magnitude of tension in rope B. So rope B is this guy right here. We could use sled 1 or sled 2. I'm going to do sled 1, okay, which is 12 kilograms. I have an applied force of 120 newtons to the right, and here's where I have to be mindful. I have a tension force, okay, in B going to the left. So when I write my F net statement, I'm going to have 120 minus the tension force in B. Okay, F net again can be replaced with mass times acceleration. The mass is 12. Make sure I have that right. 12, yep, 12. The acceleration we found already over here is 4. We have this 120 newtons, and then we have our tension in our B rope. Okay, so I'm just going to rearrange the problem. So I'm going to have the tension in rope B equals 120 minus 48. Give ourselves a little bit more room here. And then the tension force in B is going to be 120 minus that 48, so 72 newtons is the tension in rope B. Okay, so I'll give you a moment to try these. Pause and give them a little bit of thought. Number 1 is just a thinking question, okay, and number 2 is similar to the sled question we just did. They're out of your textbook, so if you want to go and find the answers there as well, you can just go and look at those. I won't do the whole problems because it'll take too long, and I have one more question to get through. Okay, so let's have a quick look. Number 1, examine each diagram in figure 8, and which rope will have the greatest tension. Okay, so in the first one, rope A should have the greatest tension because not only is it holding up the small mass that it's tied to, but it's also has to hold up all of the things behind it. Okay, so rope A should have the highest tension force versus rope B. If you look at B part with the sleds, rope A or rope B, which one should have the highest tension? Well, rope A should have the highest tension because it has to account for all of those masses behind it. Okay. Number 2, a locomotive with a mass of 6.4 times 10 to the 5th kilograms, accelerating at 0.12 meters per second squared while pulling a train car. Assume negligible friction is acting on the train. Calculate the net force on the entire train. Okay, so you could just do one system box that takes those two masses and adds them together. So that looks like it's 11.4 times 10 to the 5th kilograms. Okay, so you could take those two together. There's your mass of your system, and it's accelerating at a certain amount, so we can come up with, and I'll just do it really fast, F net equals, in this case it's just going to be our unbalanced force, so MA. So we take that mass, and I don't have a calculator handy, and we times it by the acceleration. Okay, and we get 1.4 times 10 to the 5th. Sound about right? I'll trust the book. Okay, determine the magnitude of the tension between the locomotive and the train. Okay, so again, we would model that just like the sled problems. I'm going to skip it for now. And we should get 6 times 10 to the 4th. Okay, so the last question I want to do, it does involve a slight change in direction. But it's going to follow all of the same strategies we've been using. Okay, so in this investigation we have a mass hanging over a pulley or over the edge, okay, and it's 0.2 kilograms, and it's attached to a 0.8 kilogram dynamics cart. Okay, so what I'm going to do, and this is the key piece of this, and this is all from section 3.3 if you want to go back and have a look at that. It's right out of your textbook. When this system moves, okay, there are a couple of assumptions. The mass goes down, the cart has to go to the right. Those are the only options. Okay, if we changed it and the cart went to the left, then the mass would have to go up. What we can't have is the cart can't go to the right and the mass goes up, because that would be some sort of magic. We can't have the cart go to the left and the mass go down, because that would mean the string broke or something along that line. So when we view this problem, we can have a change in direction, but the pulley and the rope is what's going to transfer the force between the two, and we do want to have some thoughts that those directions, that's why I've made them my positive directions, because they're going, the whole system has to move together. That's the key piece in this question. Okay, so the system will have to move to the right and down, or to the left and up. Those will be our options. Okay, so I'm going to go to the left and down because that's what my intuition says, and it's what most likely is going to happen. So if I look at my dynamics cart and I do a quick free body diagram, the only force that's acting on there is F of t. Okay, again, I'm anticipating that gravity and the normal force will balance each other out. So my F net statement is F net equals Ft. Replace the F net with mass times acceleration. We know the mass of the cart. But again, we hit that point where we have two unknowns in that equation, so we can't solve it. If we jump down to the hanging mass, we have an Ft and an Fg. Okay, so now when you write your F net equation for this, you'll notice Fg in this case is positive because I defined positive as being down. Okay, so Ft is negative, and this is really important because when you go to do the algebra of this, if you have these things all mixed up, it doesn't work out very nicely. When you substitute in for F net your mass times acceleration, you put in the mass of the hanging mass. I'm going to run out of room. And again, we have an equation that has two unknowns, so that poses some problems for solving. However, and here's the key, and this is how you solve this problem, the acceleration up here is the same as the acceleration here because it's system acceleration. The tension force between those two objects has to be the same. So what you can actually do is you can do a linear systems, just like you did in grade 10 math, and you can make a substitution. So we could take, in this case I've got Ft already isolated, so I can take the 0.8a and I can substitute it in for Ft. Okay, so I'm just going to rewrite that now. I'm going to take 0.2a equals 0.2 times 9.8 minus, and now instead of f of t, I'm putting in the 0.8a. Okay, now I just have to solve that problem. Okay, so I'm going to add 0.8 to both sides. So if I add 0.8 to both sides, I get 1a. Isn't that convenient? 0.2 times 9.8 is 1.96. That's an acceleration, so it's meters per second squared. So now I know the acceleration of the system. I believe I was asked for the magnitude of the tension in the rope as well. So I now have the acceleration. Got it. To get the tension, just like in math, we should have one equation here that's already isolated for tension, and lo and behold, I do. So if I take that tension force and I substitute in my newly found acceleration, then I should be able to determine the tension in that string. Okay, so nothing terribly new there. Let's say it's 1.6 newtons or thereabouts, pretty darn close. The key is thinking that the system has to move together. That idea that this has to move to the right, this has to move down, and then setting up a really good positive convention to make your life a little easier with the numbers. Okay, so I have one more here. I'm not going to do the problem, so if you could pause it and try it. It's just like the last one, and then I'll show you the answers. Okay, so hopefully you had a chance to try it. So the answers would be 3.3 meters per second squared for the acceleration. Okay, and if you add the friction piece in there, the friction piece, just so we're clear, this little friction piece right here, okay, changes the free body diagram. So there would be a force of friction here as well as Ft, and you would have a force of friction. So your F net would be Ft minus Ff. Okay, and it doesn't change the overall approach, but it does add one little wrinkle that you have to take into account. Okay, so hopefully that worked for you. Okay, and then in section 3.5, if you could try 1 to 4, those are some really good questions. Thanks for tuning in.